Bismillah wa salatu wa salam ala Rasulillah. Welcome to General Chemistry with Dr. Zainab. Today we are going to solve recitation problems for chapter 4, which is about reactions in aqueous solutions. Please keep in mind the table relative to the solubility guidelines. So anything with lithium, sodium, potassium, rubidium, cesium, and ammonium ions is soluble. Everything with nitrate, acetate, and chloride ion is also soluble. Anything with chloride, bromide, and iodide ions is soluble, except when it is with silver, mercury 1, or lead 2 ions. Anything with sulfate is soluble, except when it is with silver ion, mercury 1 ion, lead 2, calcium, strontium, and barium ion. Okay. And those who are not soluble at all are with carbonate, phosphate, chromate, and sulfide ion, except when it is with 1A family or ammonium. Anything with hydroxide ion is not soluble, except for 1A family and also for barium. Okay. Also keep in mind the activity series. So how you class the different metal relative to each other and relative to hydrogen here, which is hydrogen give 2H plus and 2 electrons. The higher you are, the easy it is for you to get oxidized. Okay, so keep that in mind. Let's start with problem number 1. 0.1025 gram sample of copper metal is dissolved in 35 ml of concentrated HNO3 solution to form copper 2 plus ion, and then water is added to make the total volume 200 ml. Calculate the molarity of copper ion in the final solution. So here we know that it dissolves in 35 ml of concentrated HNO3. We know that this is our excess reagent because it's concentrated. So all of our copper will be transformed to copper 2 ion. So let's first write the molecular equation. So we have copper solid plus HNO3 aqueous that will give copper nitrate 2 times aqueous plus hydrogen gas. Okay. Here we have HNO3. It is part of our 7-strong acid. So we know that HNO3 aqueous will ionize to give completely H plus aqueous and NO3 minus aqueous. Okay, so here I need to balance my equation by putting 2 here. So copper, 2 hydrogen gas, 2 nitrate ion, 2 nitrate ion. Okay, and we can see that here the oxidation state of copper is 0, and here it's oxidized to 2 plus. Okay, and here the oxidation state of hydrogen is +1, and it is reduced to 0. So we know that this is an oxido-reduction reaction. So we can write the half reaction. So we know that copper solid is giving copper 2 plus 2 electrons. We know that hydrogen plus H plus ion, hydronium ion, plus 1 electron should give hydrogen gas. So here I need to balance by doing 2 plus 2 electron. Okay, and then if you add it, you know that the ionic equation will be, net ionic equation will be copper solid plus 2H plus will give copper 2 plus hydrogen gas. So you can see that the nitrate ion are spectator ion. Okay, so if you write it using the molecular one, so you have copper 2H plus 2NO3 minus, copper 2 plus 2NO3 minus, and hydrogen. Okay, and the NO3 minus 2 times will be removed from both sides, and you will get the same equation. So you can use the molecular equation ionic and net ionic, or here we know that it's oxidoreduction because we know that copper is oxidized to 2 plus and hydrogen is reduced to H plus is reduced to hydrogen. So we can use the half reaction way to get the equilibrate reaction, the balance reaction. Okay, now we need to know what is the molarity. So what is the molar definition of molarity? Okay, the concentration of CO2 plus will be equal to the number of mole of copper 2 plus divided by the volume of the solution, total volume. Okay, so we need to know what is the number of mole. Here, we know that the reaction is quantitative. All of the copper is transformed to copper 2 plus. So the number of mole of copper 2 plus will be equal to the number of mole of copper solid metal, okay? And here it is equal to the mass of copper solid divided by the molar mass of copper solid. And if you check in the periodic table, the molar mass of copper solid is equal to 63.55 grams per mole. So now we have everything to calculate the concentration of copper 2 plus. So the concentration will be equal to the number of mole MCU solid divided by the molar mass of copper and 1 over the total volume. So this is our expression for the molarity of copper 2 plus. Let's get the numerical value. So the mass is 0.1025 gram. The molar mass 63.55 gram per mole. And we have the volume. So we need to have the concentration in mole per liter. So don't forget to convert 200 ml in liter by multiplying by 10 to the power minus 3. So the concentration that we were looking for, copper 2 plus, will be equal to 8.065 10 to the power minus 3 molar. Okay. 4 significant figures, 4, 4, 4. Okay. So this is a way to solve this type of problem. Always start by writing the balance equation, and you can get the net ionic equation. Here, since we know that it's oxidoreduction, we use the half oxidation and reduction reaction to get the balance equation. And from the balance equation, we know that the number of mole of copper 2 plus is equal to the number of mole of copper that was initially introduced, which is equal to the mass divided by the molar mass. Okay, and the concentration, the definition is the number of mole divided by the volume. So we divided by the volume to get the concentration. Here, never forget that the molar here is mole per liter. So don't forget to convert this volume in liter. Okay, so that's it for problem number 1. Let's move to problem number 2. How many grams of sodium hydroxide are contained in 250 ml of a 0.4 molar sodium hydroxide solution? Okay, so here what do we know? We know that we have sodium hydroxide, which is a base. Okay, and we have its concentration, which is M base equal 0.400 molar. And the volume VB equal 250 ml. Now we need to know the mass. How can we go to the mass? What is the relationship that we can use to know the mass? We know that you can get the mass from the number of mole of the compound. Okay, and here we have 2 ways to calculate the number of mole. We know that the number of mole of sodium hydroxide is in one side equal to the concentration times the volume, but it's also equal to the mass to the molar mass. Okay, and our unknown here is MB. So we can deduce MB, that it will be equal to M concentration times volume times molar mass. Okay. So we have the concentration, we have the volume, we will calculate the molar mass and then get the numerical value. The molar mass of sodium hydroxide for sodium is 22.99 from the periodic table. For oxygen, we know it now, 16.00. And for hydrogen, 1.008. And the mass is equal to 40.00 gram per mole. So we can get the numerical value of the mass. The concentration is 0.400 molar. So mole per liter, we need to convert the volume in liter. So 250.0 times 10 to the power minus 3. And then multiply by the molar mass in gram per mole. And the result is 4.00 gram. Okay, so we have 3 significant figures here. We have 4. The result should have the minimal, which is 3 significant figures. Okay, so here is just to play with the number of mole. Okay, know that you can get it from the concentrated solution by multiplying the molarity to the volume, but it's also equal to the mass divided by the molar mass. So you can deduce the mass by knowing the concentration, the volume, and the molar mass. Okay, so that's it for exercise number 2. Let's move to problem number 3. How would you prepare 2.00 liter of 0.1 molar potassium chromate solution from 1.75 molar potassium chromate solution? So here we know that we have potassium chromate. First solution that is concentrated. So we have M concentrated equal 1.75 molar. But the volume, we don't know it. From this solution, we dilute it. So we add water. To get another potassium chromate solution that is diluted, so MD equal to 0.100 molar, and a total volume V diluted, which is equal to 2.00 liter. So what is conserved between this state and this state? Exactly the number of mole. We know that the number of mole of potassium chromate in the concentrated solution should be equal to the number of mole of potassium chromate in the diluted solution. Okay, so I just have a concentrated solution like this. Okay, and I add water to get something diluted. But the number of mole here will be the same, but the concentration is less. Like you have less particles per unit volumes, but the number of particles you can say is the same. Okay, the number of mole is the same. Okay, so that's why the number of mole is conserved. Here is the concentrated 1.75 molar. You have more particle per unit volume, and here you have less particle per unit volume, 2 liter. Okay, so this is why this is conserved. So what is the number of mole in the concentrated solution? Is MC, VC, okay? And what is the number of mole in the diluted solution? MD, VD. What is unknown here is VC. So let's remove, get VC from this equation. MG, VD divided by M concentrated, okay? We can get the numerical value of the volume. MD is 0.100 times here the volume 2 liter divided by MC 1.75. So here the volume is in liter. This is molar. Molar, it will cancel out. So the volume will be given in liter. The direct result that I get is 0.114 liter, and this is the same as 114 ml. Okay, so this is to understand how you get a diluted solution from a concentrated solution. Okay, we know the concentration of the diluted solution and the total volume. We know the initial concentration of the concentrated solution, so we can know how much of that solution we should take and then add water to get our diluted solution with the good concentration and volume. Okay, so this is the way actually that you will do it in the lab. I will give you a concentrated solution and I tell you to prepare this solution. So you need to do this calculation to know that you have to take 114 ml of the concentrated solution and add it diluted with water to go to 2 liter, and that solution will be 0.100 molar. Okay. Let's move to problem number 4. A solution is prepared by dissolving 10.8 gram of ammonium sulfate in enough water. So we have 10.8 gram of ammonium sulfate. in enough water to make 100.0 ml of stock solution. A 10.00 ml of that stock solution is added to 50 ml of water. Calculate the concentration of ammonium ion and sulfate ion in the final solution. Okay, so we have a solution that is prepared by dissolving ammonium sulfate. So what is this formula for ammonium sulfate? Ammonium 2 times sulfate SO4. So how did we prepare this solution? By dissolving a mass M, 10.8 gram, and in enough water to get a 100.0 ml stock solution. Okay, then we take a volume V1 equal 10.0 ml of this solution. Okay, and of that solution is added to 50 ml. So we add 50 ml of water. This is how you do sequentially. You just translate all of the data in sequentially, and then you know that we have the solution first. Then from the solution, we take V1 10 ml, we add 50 ml of water. Okay, and then what is asked is what is the concentration of ammonium ions, meaning NH4 plus, we don't know it, and the concentration of sulfate. Okay, so how can we do that? How can we do that? This is our concentrated solution actually. Okay, so we have MC and VC. Okay, and from this solution, we take only V1 equal to 10 ml. Then we add 50 ml. So the total solution, V total or V diluted, will be equal to 60 ml. Okay, this is 15.00, okay, and 50.00. Okay, it's important to get the significant figures. So here we have 60.00 ml, which will be the total solution. But we don't know yet what is the concentration of the diluted solution. And from this diluted solution concentration, we will deduce what is the concentration of the ammonium ion and the sulfate ion. Okay, so let's translate our data into concentration, because here we have masses. So we know that the concentration of ammonium sulfate concentrated, I call it big MC, will be equal to the number of mole divided by the volume. Here the number of mole is the mass to the molar mass. So MC molar mass times the volume. So this will be VC. And this concentration, I will take M1. I put M1. Okay, so because the concentration here, MC, will be equal to the concentration of M1. Okay, I took V1 equal to 10 ml of that solution. So the concentration is the same. Then it diluted to 60 ml. So you have the VD. Okay, so here to calculate the concentration, we need the molar mass. So let's calculate the molar mass of ammonium sulfate. If you calculate it, you will get 132.08 per mole. Okay, so the concentration of the initial solution will be equal to the mass, 10.8, divided by the molar mass, 132.08, times the volume here is 100 ml. Don't forget to convert it in liter. 10 to the power minus 3. And the concentration will be 0.818 molar. So I know the concentration of the volume that I took. And then this one is diluted to 50 ml. What is conserved in between is the number of mole. Okay, the number of mole is a concentrated solution will be equal to the number of mole in the diluted solution. Okay, and the expression is MC. Here, what is the volume that I take? V1. Okay, this is V1 that I diluted will be equal to MD times VD, and VD is 60 ml. Okay, so I can deduce what is the concentration of the final solution. MD equal MC V1, okay, divided by V diluted. Okay, so MD will be equal to, what is MC that we calculated? 0.818 multiply by 10 ml that I took. So 10.00, 10 to the power minus 3 in liter, divided by the volume of the diluted solution, which is 60 ml, 60.00, 10 to the power minus 3. So this one, they cancel out. So the concentration of ammonium sulfate in the diluted solution is equal to 0.136 mole. Okay, this is equal to the concentration of ammonium sulfate after dilution. Okay. Now from this, how can I know the concentration of ammonium? I know that the concentration of ammonium plus will be 2 times MD, because I have 2 times more ammonium ion than the ammonium sulfate. Then this will be equal to 0.272 mole. In the other side, the concentration of sulfate ion is exactly equal to the concentration of ammonium sulfate, and this is equal to 0.136 mole. Okay, how do I know that? Because if you have ammonium sulfate and you dissolve it in water, you will have 2 times ammonium plus SO4 2 minus. So I have 2 times more ammonium than sulfate. If I have the concentration of this one will be 2 times, so 2 MT, and this one will be the same concentration. Okay, so that's it for problem number 4. Let's move to problem number 5. When the following solutions are mixed together, what precipitate will form? So we have A, B, C, and D. Here we need to remember our solubility guidelines. Let's start by number 1. We have nitrate. We know that anything with nitrate is soluble, so we don't have problem with mercury 1 nitrate. It will be soluble. We have copper sulfate. For sulfate, we need to be careful. Anything with sulfate is not soluble except when it is with anything with sulfate is soluble except when it is with mercury, silver, and lead. Okay, so here we need to be careful since we have mercury. Okay, so we know that if we have mercury 1 nitrate plus copper sulfate, this will give copper nitrate. So remember, this is plus, the ion, so it's 2 plus, okay, and you have copper 2 plus. So you trade the ions, so a nitrate will go to copper, and then sulfate will go to mercury 1, so plus mercury sulfate. We know that mercury sulfate is not soluble, so this will precipitate. Okay, For this one, we will have a precipitate. This is A. Now for B, we have nickel nitrate. So anything nitrate is soluble. We have calcium chloride. So here it's nickel nitrate 2 times. They react with calcium chloride aqueous. Okay. So and one thing I wanted to say here, so you have all of them that are already oxidized. So here you have mercury 1, 2 plus and copper 2 plus. Here you have nickel 2 plus and calcium 2 plus. Okay. Here you have carbonate with potassium and magnesium 2 plus. Okay, here you have the chromate ion and aluminum 3 plus. Okay, so here we don't have oxidoreduction reaction, we have replacement reaction, meaning here, as you can see, you have mercury 1 with nitrate. So this one, the nitrate goes to copper 2 plus, so you have copper nitrate, and the sulfate goes to mercury 1, so you have mercury sulfate. Okay, for B, it will be the same. So we have nickel nitrate, aqueous, so anything with nitrate is soluble, plus calcium Cl2 aqueous. Anything with chloride is soluble, except when it is with mercury, silver, and lead-2 ions. Okay, so here we don't have any of those 3 ions, so we know that it's going to be soluble. So we'll have nickel that go with chloride, and it will be soluble, aqueous, plus calcium nitrate. So in this one, no precipitate. Everything is aqueous. For C, we have potassium carbonate. So anything with potassium is soluble, plus magnesium iodide. We know that for iodide, the ones that are not soluble are with the 3 ions, silver, mercury 1, and lead-2 here. So this one is soluble. When we will trade ions, we know that potassium will go to iodine or iodide, and we know that anything with potassium will be soluble. So we have Ki we'll balance the reaction later. Plus, we have the magnesium with the carbonate. So remember that for carbonate, anything with carbonate is not soluble, except when it is with 1A. Okay, 1A like potassium, sodium, cesium, rubidium. So here we will have magnesium carbonate that will be solid. And here we need 2 times potassium iodide to have something that is balanced. Okay, aqueous. So here this will be our precipitate. Now the last one, we have sodium chromate that react with aluminum bromide. Okay, and here we have sodium. Anything with sodium is soluble. Anything with bromide is soluble, except when it uses our 3 ions, which are silver, mercury, and lead. So here this one is none of them, so it's soluble. Here we'll have aluminum that will go with chromate. Remember, chromate is like carbonate. It's soluble only when it is with 1A. Okay, so now when you have aluminum chromate, it's not going to be soluble. So we have aluminum 2 times chromate 3 plus we have sodium with bromide that is soluble. Sodium bromide, and this is aqueous. So we need to balance our reaction. You have 3 times here. You have 2 times aluminum bromide. That will give here 6. And for aluminum, 2 chromate. Okay, so we have 3 chromates, 3 chromate. We have 2 aluminum, 2 aluminum. Here 6 sodium, 6 sodium, 6 bromide, 6 bromide. Okay, and this will be solid. So this will be our precipitate. So here you can solve it using this table easily. Okay, so we use that, the fact that anything here with lithium, sodium, potassium, rubidium, cesium, and ammonium is soluble. All of the nitrate that we had were soluble. When we have chloride, iodide, or bromide, we need to check if you don't have any of these, silver, lead 2, or mercury 1, it's going to be soluble. If you have one of these 3, then it's not going to be, it's not soluble. Okay, if you have the sulfate ion, anything with sulfate is soluble except when it is with silver, mercury 1, lead 2, calcium, strontium, and barium. Okay, we also use the fact that anything with carbonate is not soluble, anything with chromate is not soluble, except when you have a lithium, sodium, potassium, rubidium, cesium, or ammonium ion. Okay, so we use this table to solve problem number 5. Here. Okay, so that's it for this one. Let's move to problem number 6. What mass of sodium chromate is needed to precipitate all of the silver ions from 75.0 ml of 0.1 molar solution of silver nitrate? Okay, so what is going to happen? We have, what do we have? We have a solution of silver nitrate here. Okay, silver nitrate. Then we will add sodium chromate. So what will happen? We can write the reaction. We know that sodium, we already write it from the previous slide. Sodium chromate will react, this is aqueous, anything with sodium is soluble, plus silver nitrate, anything with nitrate is soluble. Then we will have silver chromate. Two times, plus sodium nitrate. Okay, we can balance our reaction. Sodium nitrate here. Silver we have 2 times, so we need here, okay, 2 times silver. Chromate, we need 2, we need 1 here, chromates. Sodium 2 times, sodium 2 times, 2 nitrate, 2 nitrate. Okay, so our equation is balanced. What will happen to silver chromate? We know that anything with chromate will not be soluble. Here, you can remember the table. Anything with chromate is not soluble except when you have lithium, sodium, potassium, rubidium, cesium, or ammonium. So here we have silver chromate. So we know that it's going to be solid. Anything with nitrate is soluble. So this one is going to be aqueous. Okay, so this is our setup. Now, what we have is we have sodium chromate. And what is asked is the mass. And this is added to a solution of silver nitrate. And we know its concentration, V2. So here I will call it M1. V2 equal to 75.0 ml. So this is the solution of silver ion. And the concentration, M2, 0.100 molar. Okay, and this will give, we know, precipitation of silver chromate. Okay. Yes. Now the question is asked is the quantity of sodium chromate that we use. Okay, we know that the number of mole N1 divided by 1 should be equal to the number of mole of 2 divided by 2. 2 here is silver nitrate, okay, at the equivalence point when they are used in the stoichiometric amount. So here we can deduce N1 equal to N2 divided by 2. What is the number of mole of silver nitrate that we have? It's concentrations times volume, M2, V2. But how can we deduce it from the mass of sodium chromate? the number of mole, will also be M1 divided by the molar mass of 1. So we can deduce the expression for M1, M2, V2, molar mass of 1. So this is the expression of our mass. Now let's calculate the molar mass of sodium chromate. If you calculate it, this is equal to 161.98 grams per mole. So we can get the numerical value for M1. M2 equals 0.100. V2 here is in milliliter. Don't forget to convert it in liter. And the molar mass 161.98. So we use a mass of sodium chromate, which is equal to 0.607 grams. Okay. So whenever you have this type of exercise, just like make yourself know what you did actually. So you have a silver nitrate solution, you add sodium chromate. So you can write the molecular equation. We have sodium chromate that will react with silver nitrate to give silver chromate solid plus sodium nitrate aqueous. Okay, and then you can have the stoichiometric amount. We know that the number of mole of sodium chromate divided by 1 should be equal to the number of mole of silver nitrate divided by 2. So we can deduce the number of mole of sodium chromate when we are at the equivalence point or in the stoichiometric amount. We have the two expressions, the concentrations times the volume, but also the mass divided by the molar mass. Then we can deduce the expression for the mass. And this is how you can solve this type of problem. Always start by writing the balanced chemical equation. That is the basics. Okay. Let's move to exercise number 7. What mass of solid aluminum hydroxide is produced when 50 ml of 0.2 molar aluminum nitrate is added to 200 ml of 0.1 potassium hydroxide? So we know that we have a solution of aluminum nitrate, concentration M1 equal to 0.200, volume 50.0 ml, to which we add solution of potassium hydroxide with a concentration M2 0.100 and a volume V2 200.0 ml. And this will produce aluminum hydroxide, which will be solid. So let's write the balance reaction. So we know that aluminum nitrate, anything with nitrate is soluble, so aqueous, plus potassium hydroxide, anything with potassium is soluble, aqueous, will give aluminum hydroxide, which will be solid, plus potassium nitrate. But let's balance our chemical equation. We have 3 OH, so we need 3 here, 3 potassium, we need 3 here, 3 nitrate, 3 nitrate. Our equation is balanced. So we have a reaction where the number of mole of both reactants have been given. So what do you do first? We need to check what is the limiting reagent. So from our chemical equation, we know that N1 divided by 1 should be equal to N2 divided by 3. So let's compare these two values. N1 divided by 1 is N1, and this is equal to M1 V1. This is equal to 0.200 times 50.0 10 to the power minus 3. And this is equal to 0.0100 mole. N2 divided by 3 will be equal to M2V2, number of mole, divided by 3. So this is equal to 0.100 times 200.0 10 to the power minus 3 divided by 3. This is equal to 6.67 10 to the power minus 3 mole. We see that this one is smaller than the N1 divided by 1. So N1 over 1 is bigger then N2/3. This means that aluminum nitrate is in excess, and potassium hydroxide is the limiting reagent. So my number of mole will be determined by the number of mole of potassium hydroxide. Okay, and I know that N2 divided by 3 should be equal to N aluminum hydroxide divided by 1. And the number of mole of aluminum hydroxide is equal to M divided by the molar mass. So I know that the mass of aluminum hydroxide will be equal to N2 divided by 3 multiplied by M. So N2 times the molar mass divided by 3. We can get the numerical value. So M, know that M2 is 6.67, 10 to the power minus 3. The molar mass of aluminum hydroxide is equal to 78.00 and divided by 3. And the numerical value is M equals 0.520 gram. So the same principle that we use for chapter 3, when we have a reaction and the number of mole of both reactants have been given, the first thing you need to do is to check the chemical equation and the reaction is balanced. Then you calculate the number of mole of each of the reactant and check which one is the limiting reactant and which one is in excess. Then you can deduce from the limiting reactant the number of mole of the products that you need to calculate. Okay, so it's the same principle that what we did also in chapter 3. Now let's move to exercise 8. What volume of 0.02 molar calcium hydroxide is required to neutralize 35.00 ml of 0.05 molar nitric acid? So here we have a neutralization, meaning we have a base, calcium hydroxide, that will react with nitric acid, which is our acid. So we have calcium hydroxide, and we have the concentration, MB, 0.0200 molar. And what we are looking for is the volume. We don't know what is VB for the time being. And it is added to a solution of nitric acid, so HNO3 from nitrate. Okay, we have the concentration, MA, 0.0500 molar, and we know the volume of the acid, 35.00 ml. Okay, so this is the setup. What you should do first, write the molecular equation. So calcium hydroxide will react with HNO3 to give calcium nitrate times plus water. Okay, and we know that this is aqueous. Anything with nitrate is solid, aqueous. Okay, and this is dissolved. Here we need to balance our chemical equation. We have 2 nitrate, so we need 2 nitrate. We have 2 hydrogen, 2 hydrogen. We have 2 OH, so 2 OH here, so O 2 times and H 2 times. Okay, so we have H2, H2O, we need to multiply here by 2. So we have 4, 2 plus 2, 4, and 2 times oxygen, 2 times oxygen. So our chemical reaction is balanced. Now we know that it's balanced. So this is the setup. The chemical equation is balanced. We know that at the neutralization point, we have MBBB over 1, which is the number of mole of calcium hydroxide, should be equal to MAVA, which is equal to the number of mole of nitric acid divided by 2. Our unknown here is VB. So you know that VB will be equal to MA VA divided by 2 times MB. So if you don't write the chemical equation, this factor 2 will be missed. Okay, so it's good to get the setup what you have, know that this is the base, this is the acid, then you write the chemical equation, you balance it. And then from the balance equation, you know that at the neutralization point, the number of mole of the base divided by 1 should be equal to number of mole of the acid divided by 2. Then you can deduce the unknown that you have. Here, if you calculate it, MA, we know that it's 0.05 times VA 35.00. And here is 2 times 0.0200. Okay, if you want, you can have it directly in liter. Okay, and VB will be equal to 43.8 ml or 43.8 10 to the power minus 3 liter. Okay. So if you don't use the chemical equation and balance it, you are not gonna be able to solve this type of problem. So always check the setup and write the chemical equation, and then use the relationship between the number of mole and the concentration and the volume, and you can easily solve this type of problems. Okay, let's move to the last problem, problem number 9. So hydrochloric acid is 75 ml of 0.25 molar is added to 225 ml of 0.055 molar of barium hydroxide solution. What is the concentration of the excess H plus or hydroxide ion left in the final solution? Okay, so let's make the setup. We know that we have hydrochloric acid, HL, which is our acid. We know that the concentration is MA, 0.250 molar, and the volume VA, 75.0 ml. And it is reacted with barium hydroxide, which is our base, so with the concentration MB 0.0550 molar, and a volume 225.0 ml. And we need to know actually which reactant will be the excess reactant, and then you can know what is left. Okay, now let's write our chemical equation. HCl plus barium hydroxide 2 times will give barium chloride, okay, plus water. Okay, and this is aqueous, strong acid. Barium with hydroxide is soluble. Barium chloride is soluble. We can balance our chemical equation. So we have chloride 2 times here, 2 times. And we have 4 hydrogen and 2 oxygen. We need 2 here. 4 hydrogen and 2 oxygen in both sides. Now my chemical equation is balanced. We know that at the neutralization point, we will have N acid divided by 2. That will be equal to N base divided by 1. So we need to compare N acid divided by 2 and N base divided by 1. Na acid divided by 2 is Na Va over 2. This is equal to 0.1250 times 75.0 10 to the power minus 3 to have it in mole divided by 2. And this is equal to 9.38 10 to the power minus 3, sorry, mole. And we know that NB is equal to MB VB, and this is equal to 0.0550 times 225.0 10 to the power minus 3, and this is equal to 0.0153 1.24 molar, or 1.24 10 to the power minus 2 mole. So what do we see? We see that NB divided by 1 is bigger than Na divided by 2. So what is our limiting reactant? The acid HCl is the limiting reactant. Or you can say that barium hydroxide is in excess. Okay, so we know that all of the acid will react. So what will be left in our solution will be OH minus. Okay, so we can calculate that. The total quantity of barium hydroxide to react will be equal to Na over 2. Okay, so we know that the number of mole of base left will be equal to the number of mole of the base initially that we have, which is MB BB, minus the number of mole of the base that reacted, which is equal to MA VA over 2. Okay, so this is the number of mole of barium hydroxide that is left. Okay, but here what is asked is the concentration of excess OH minus. Okay, I have barium hydroxide. If it goes underwater, it will give Ba2 plus 2 OH minus. What I mean is from the concentration of the leftover barium hydroxide to get the concentration of hydroxide ion that are left, I need this factor 2. Okay, because I know that the concentration of HO minus will be equal to the number of mole of HO minus divided by the total volume of the solution, V total. So VA plus VB. Okay, this will be the concentration. Now we need to calculate the number of mole of OH minus. Okay, we know that here number of mole of barium hydroxide divided by 1 should be equal to the number of mole of OH minus divided by 2. So the number of mole of OH minus will be 2 times. Okay, this is where you get the 2 times. So here we will have 2 times MB VB minus MA VA over 2 and divided by the total volume, which is VA plus VB. Okay, so you need to be careful about the number of mole of the concentration of HO minus. Okay, it's coming from this leftover, so you have barium hydroxide that will dissolve to give barium 2 plus and 2 times OH minus. So from the chemical equation, you know the number of mole of OH minus with this is left. Okay, this is the left. What is leftover? Okay, and this is what we calculate. The number of mole of base left is equal to what we put initially minus what reacted, and we know that all of the acid will react. And at the neutralization point, this is exactly equal to the number of mole of barium hydroxide that reacted. Okay, but we have here the 2. The 2 is coming from the chemical equation of barium that is dissolving to give barium hydroxide to give barium and hydroxide ion. Okay, and you can calculate the concentration of HO minus. So 2 times MBVB, we calculated 0.124 minus MAVA over 2 is 9.38 10 to the power minus 3 divided by the total volume here, which is equal to, so the 10 to the power minus 3 will be here 22. What is the volume? Okay, 225.0 plus 75.0 10 to the power minus 3. Okay, to get it in liter, and the concentration will be equal to 0.0 200 molar. Okay, so that's it. So this is the good training for you to get the chemical equation and determine which one is the limiting reactant, and you know how to calculate the leftover of the excess reagent, and from the leftover of this excess reagent you do the decomposition to have the barium and all of the ions that are produced. From there you can calculate the concentration of the leftover HO minus. Okay, that's it for the recitation of chapter 4. See you again next time, inshallah.